Recording, great. And then today we're going to talk about debugging. So how many of you guys have used a debugger before? Not too many. That's okay. How many of you guys do printf? Like you print debug. And then the rest of you, what's your strategy? Look at it really hard? I know I've tried that one. That one tends to be the worst one. You squint, you're like, what's wrong with you? You give it the mean look. So one of the reasons that we need to debug is that when we write code, we tend to believe we are writing the correct solution, right? Most of us aren't spending our time, wasting our time writing down the wrong answer to the problem. And so when we run our program, though, we find that our expectations are not met, right? We thought we wrote the right thing. We run our program, and it's like, no, it's not passing this test case. It's doing something wrong. It has some bad behavior. And so we have this contradiction between our expectations and what's really happening. And that's kind of jarring. This is why sometimes you might go and look at your program and be like, you are correct. Why aren't you working right? Like it's somehow like the computer is misinterpreting the commands that you told it to do, not that you might have screwed up in writing the wrong commands, right? And so we need something to point out to us where things are going wrong. We need to be like, okay, you meant to do this, but look, this is what's actually happening. And that's what the debugger is going to allow us to do. It's going to demonstrate to us where things are going wrong. So some of the advantages of using a debugger is you don't need to add print statements everywhere. That's probably pretty annoying when you're trying to find the problem, or to try to figure out what your problem is. Right? You're like, okay, put some print statements in some spots. Okay, great, I found my problem. I think I got it taken care of. Great, take out all the print statements. Oh, there's still more problems. Put those print statements back in, and then in and out, in and out. And that's really annoying to have to do. I've also had it where I've added print statements to my program, and I actually introduced more bugs into it because I misused pointers in there. Or, for example, like you're trying to figure out what might be wrong with this pointer, and you might accidentally dereference it, and it might not be a good pointer. So you're introducing more bugs into your program. But if you're using the debugger is just going to print out the values for the variables for you. And even if you print out something that would be illegal, it's not going to crash your program. It'll just say, I can't display that. This memory is not accessible, which is really nice. The other thing that's really great about the debugger is you can often pinpoint the exact line of code a segfault is happening on. You run the debugger, and it'll stop you at the line. Oh, the segfault happened on this line of code right here. You access memory that you didn't have access to. And then that problem might be on that line of code, or it might be on some other line of code, right? It might be that you didn't allocate enough space for your array, and so now you're going out of bounds. Or maybe you might have made a mistake on your conditional expression like I made earlier, and you're going out of bounds because of that. Or there could be a handful of other things, but at least you have an idea of what variable is going wrong. Debuggers can take some time to learn how to use, but the time that you put into learning how to use them is definitely well worth it, and you're definitely going to recoup that later on when you're using it to solve the problems that you run into. So debugging is really an art, and it's locating where your program's behavior deviates from your expectations. And so to be able to do that, we need two different things. We need the ability to pause our program at certain points so we can figure out what's going on. And then we also need the ability to examine the values that are there. And so you just need to know, you need to have a really good idea of what should be happening, and then look at what is happening and see where those two things are deviating from. And it can take a bit of time to pinpoint where your error is actually happening. Normally, you're going to have some idea of where your bug is happening at, and so you can go set breakpoints, I'm going to show you in a second, around that area. Hold on. No, this is the wrong problem. Okay. Oh wait, I also want to. No, I want to revert him too. So the way that you can set breakpoints here in CLion is by clicking to the left of the line where you want to stop. So if I set a breakpoint here and then I run my program through the debugger, When it reaches this line of code, it's going to pause here. And then it's also going to show me the values of variables. I'm going to be able to print them out. The nice thing here is I don't have to put any print statements here or tell it to pause here by adding any extra code. It'll just do it itself. So if I click debug, it's now going to get, or at least try to get to that line of code, but oh, there's problems in this code. So this program has a lot of errors in it, and we are going to need to find at least some of them. So I might set a breakpoint here on line 65 because we weren't able to get to 66 and try debugging again. And so now we pause and we're able to see the values of some of the variables. Some of these other ones are ones that I've created earlier. So you can see well, what's the value of len or AR or argv? Len and AR probably aren't too useful right now because they're not initialized. But we can see things like argument count, 8. We've got 8 arguments. We can also look at argv. If there's some value here that's not shown that you're interested in and you want to see it, you can go to plus here and you can type that expression. So if I want to see what's argv at 3, I can type that in there and I can see that argv at position 3 happens to be the number 3. The expressions here can be as complicated as you want. I want to know what is argc plus 27 minus 16 divided by 33. You can go as crazy as you want with the expressions here to see what the evaluation is. And then it'll keep showing that value for as long as you want it to be there, and you can delete it when you're done with it. A lot better than adding in a print statement to get it to show up. The other thing is you may or may not have an idea of where your bugs are happening at. And if you don't have an idea of where your bugs are happening at, what you can do is you can look at your program and set a breakpoint in the middle. Once you reach that point of code, you check to see if the program state is what you expect. If everything is good, where does it mean our bug must be at? The second half. If stuff is not good, where must it mean our bug is at? The first half, right? And let's say it happened to be in the first half. What I could do is I could set another breakpoint halfway in between that first breakpoint and the start. And now if I get to this point in my program and everything's good, it must mean my bug is where? Second half of this statement, right? Down here. Or if it's not, it must be up here, right? And so you can narrow down quite quickly where your bug is happening at by setting breakpoints at the halfway execution point. Now, one of the key things is that it's the halfway point of execution, not halfway down your file. I don't imagine when the last time you've written a program where the halfway execution point was halfway down the program or halfway down the file, right? For me, main is calling 3 functions, so my halfway execution point is actually line 66, right? Halfway through the program. And we saw before that we weren't even able to reach line 66. So we know our problem must be either on line 65 or inside the parse args function. The goal of this program is to take the arguments that are passed on the command line, sort them, and then print out the result in that sorted order. If you are here in C-line and you want to pass command line arguments to your program, you go to Run, Edit Configurations, and then in Program Arguments, you enter them here. So if you're doing the second and third problems for your homework and you want to be able to pass in those arguments in C-line, you go and you put them in this area. If your arguments have spaces in them, remember spaces separate each argument, you'd have to put in quotation marks. So if I wanted 12, 45, and 3 as one argument, I would need to put them inside quotes. And so now this is 12 space 45 space 3 is one argument as opposed to being 3 separate. This is going to be really useful for those of you who happen to have spaces in your path when you're running your program. Also, you should pay attention that when your program runs, it's actually going to run inside this directory, cmake build debug. So if you're specifying past the files, it needs to be either relative to this directory's location, or you can just give the absolute path, and that one's always going to be good. So for movement, once you've paused, right, you're able to look at the values of the variables and see if everything makes sense. For movement here, you have a couple different options. They are this button over here, resume, step over, step into, and step out of. What resume is going to do, it's going to bring you to the next breakpoint that the program is going to encounter. Or if there are no breakpoints, it's just going to run the program until the end. Step over and step into both will run the current line of code that you're on, and pause on the next line of code that comes after. But they have a little bit of different behavior when that line of code is a function call. If that line of code is a function call and you do step over, you do the entire function and you go to the next line. So if I do step over right now, it's going to do the entire parse args and then try to pause on line 66. But if I do the step into is going to try to go into the function and pause at the first line of code of that function. So if I step into, if I do a step into right now, it's going to go inside of parse args. There's also step out of, which will complete the function that you're running, the function that you're in right now, and it will pause on the line of code that it returns from, or that it returns to. Are there any questions about these different ways of traversing through the file or through your program once you have it paused? So on both on lines of code that aren't function calls, step into and step out of have the exact same behavior, and they just do that line. So if I was on line 64 and I did step over or step into, it would just do that line of code and move me to line 65. Yeah. So the question is if you're recursing, right, and you're really deep in the recursion, like 5 levels down, and you do a step out of, will it bring you all the way back out to the very top, or will it bring you just up to the next level above you? It'll just bring you to the function that called you, which is yourself. So you would go from like being 5 levels deep to 4 levels deep. Also, you can see over here is the stack frame, and so I can move in between it. So let's say I step into a parse args. Now notice I'm inside parse args, right? You can see that down here. If I want to go back to main and see what main's value is, like the values of like main's local variables and stuff, I can click on main. It's going to bring me back to main. So in your question with the recursion, right, they'd be like, level 1, 2, 3, 4, 5. You could go back to each one of those levels and see what was happening on each one. But like if I go back here, I can't continue movement because I'm inside parse args. I have to keep running from there. That's a great question. Anything else? So the goal over here in this function right here is that it's supposed to take in the command line arguments, which are, again, an array of strings, and we actually want to turn them into an array of numbers. And so we're taking our command line arguments, argc and argv, and we want to fill in array with, we want to make space for array and fill in array with the numeric values and set len equal to the number of values that are there. The first thing that I do is I set len equal to argc minus 1, and that's because the first command line argument is actually the name of the program, and I don't want to store that into my array of numbers. So I subtract 1. I then try to make space for my elements, and then here's the function that we mentioned at the very end of class today, scanf. I'm trying to convert each one of those arguments into their numeric form, and then add it to the array. So we do the first one, and we do the second one, and then we crash, right? So there are some problems in this function, and I want you guys to see if you can pick up on what any of them are. And I'll make us pause right here as we debug again. And we're going to go into the program once more. And I will get rid of this breakpoint and then resume. And it's going to cause me to pause here. Some things that we might want to help us figure out if stuff is working correctly is we want to be able to look at more of the variables. So here we can see like what is the value of I, but we're probably also interested in what other expressions here to see the values of. We might, well, we have len down here, but we're probably interested in star len, right? So if we want to add star len, we would just go over to our watches, add one more watch, and say star len. And we can see that len's value is 7 and argc's value is 8, so that's being updated correctly. Anything else that we might want to see? I, right? So we can see I, so we can add I in here. So I won't show up right away because it's declared inside this for loop, and so I only exist while the for loop is running. After the for loop completes, I will disappear. But if we step into the for loop, you can see that I does exist, and it has the value 0. Anything else that you might be interested in seeing? Yeah, we're probably interested in seeing something like argv at I, right? And we might be interested in seeing all the arguments. So we can definitely do argv at I here, and just by doing argv at I. You can also highlight an expression over here in the debugger. Oops. Okay, so you highlight the expression, then you can right click, and you can say add to watches, and it will also cause that expression to show up there too, so you don't have to keep typing it over and over again. Unfortunately, there's no command that will let us see all of the elements at once. But what you can do, or at least inside GDB or inside CLion's interface, but CLion runs on top of GDB, and if you know GDB commands, you can actually go to the GDB terminal and enter them. So one cool trick that you can do is you can do your array, in this case argv. You can say where you want to start. I want to start at the beginning, and then you can say at how many things you want to see. So I want to see argc things probably. Oops. I got to do P to get it to print out. And now I can see the values of all of my arguments. And this only works for like a single dimensional array. So if you wanted to see like a multi-dimensional array, all of its values, it won't work. But what you could do is you could do one row at a time to get it to print out. So right now I is 0. And what's argv at I? No, it's a pointer to the string, right? Because argv at 0, what I say argv at 0 is? The name of the program, right? And I probably don't want to copy the name of the program over here, right? I probably want to start copying not at argv 0, but at argv 1. So what can I change in my code to get that to happen?
I equals 1.
So setting I equal to 1 would actually be incorrect.
Okay.
Because here we'd be putting it at the wrong location, right?
No, wait, that's I plus 1.
Yeah, we can do over here, we could do I plus 1, right? Because I still want to start putting elements at the beginning of my array, right? Because if I started putting them at 1, element 0 would be empty and then things would be off. Yeah. So great, we fixed that problem. And so we need to stop debugging and go through again. And now we're probably also interested in seeing maybe not what argv at I is, but we probably want to see argv at I plus 1, right? Okay, can I edit this? So we'll change this to argv at I plus 1. Hey, we can see there's a number there, which is good. So we try stepping over. Oh, now it crashed the first time. So there's still more mistakes over here. There's actually a lot of mistakes in this one small section of like 3 lines of code, 4 lines of code. Yeah, we forgot to multiply by the size of the thing, right? No, remember I told you like this is a really easy mistake to make. And so what should we use instead of malloc? We can use calloc, right? Because as soon as I say, hey, I want to do calloc, and I try to like compile now with that in there, it's going to be like, oh no. Hey, calloc wants 2 arguments, right? And so it helps us catch that error by doing that. So we can do, we want len things, but here, what should, oops, go away. We want the size of, we can do int, but in general, the way not to screw up ever is star AR. You'll never screw up on the type if you do star whatever the thing over here on the left is. But yes, int would also be valid too, and it gives you the exact same thing. So now we're making the correct amount of space, and let's see if that fixes things. So we're going to step over, and here we crash once more. So I know, right? Like, how can I make so many mistakes? Intentionally, yeah. No. Notice we didn't even get past the first iteration, right? Here we're on iteration 0, and as soon as I tried to do this line of code 56, it broke, right? So where must our mistake probably be at this point in time? Given that I is 0, argv at I plus 1 is a valid number, where's our mistake probably at? Well, no, but we didn't even get past I is 0. And I is 0 is in bounds.
Pointer.
Yep. Right, so we need the address of. And so one of the things that would help us catch these mistakes, and what I highly encourage you to do, is to turn on the warnings. Right? I turned them off just so that that mistake wouldn't come up. So what we would do to turn on the warnings is we do a target compile options. We say the name of our executable that we're trying to work on. Right now we're working with current. So current and then private dash wall to turn on all the warnings, and then dash w error. So now we can reload those changes. Reload those changes. Thanks. And now if we go back to main.c and let's say, oops, I try getting rid of that ampersand, and notice it's now a red error. And so if I tried to build, it's going to be like, hey, I want an argument of type int pointer, but your argument has type int. So it complains and stops about it. So the compiler can be your friend in helping you catch some of these bugs. So then let's go again. Oops. Okay, that is a spurious complaint. Initialize that. Okay, so we get inside our function, and hey, didn't crash this time. And so now we might also be interested in seeing what is array at I. So we'll add that watch in there and see what happens. Right now, we just read in 12, and so we got 12. We just read in 45, and we got 45. I'm looking right here. Right, so it seems to be working at this point in time. We're getting the values in. One thing you can do that's pretty cool is maybe we want to stop in this loop or stop somewhere, but we only want to stop there some of the time. You can set on the breakpoint, after you set it, you can right click on it and you can add some conditions. Like, hey, I only want to stop when I is greater than or equal to 4. And now this breakpoint in here is only going to stop when I is greater than or equal to 4. And that expression can be as complicated as you want it to be. So this is really good if you want to stop in a loop, but like your loop is failing, but like some way into it. Like I have a loop that runs 1,000 times and it fails after iteration 700, right? Sucks have to go through 700 of them manually. Just set a condition that says I is greater than or equal to 700, and you'll stop there. This is also good if you know your function is breaking on a particular set of arguments, right? You might be using this function a whole bunch and it's being called in a lot of different areas. And most of the time it works, but when it gets called with this particular set of arguments, it breaks. You could set a breakpoint inside that function and make it conditional and say, I only want to stop here when the function is called with x, y, and z. And then it'll stop only on the time when it's called with the things that break it. The other nice thing is you'll also have the stack trace over here. So you can see where that call came from too by tracing it back up to know which piece of code was actually calling it. We said in our example it's being called from many different areas. So there's that option. So now that we're done with it, let's try stepping out, finishing the function. Hey, we got to the next area. But if we look at AR, what's its value? AR is right down here. Or you could read it up here. No, but didn't I just set it? Right? I could have sworn that if I go back and redo it again, and let's say I set a breakpoint here at the end of my function, line 59, and I resume. I'm pretty sure that if I go over here and look at AR, well, AR is not null here. And if I print AR's elements, so P AR at 0 at star len, those all look good. So why is it that after I come out of my function, AR is null? Yeah, right. So again, remember, we said that we want to change AR inside of our function, right? What's AR's type? Integer pointer. So if I want to be able to change my integer pointer inside my function has to accept a integer pointer, right? Is there an ampersand? Well, yes, we do, but like our mistake was in one, assuming that our argument here should have been of type integer pointer when we wanted to change the integer pointer that we have here in main. Again, if we want to change something of type x, we have to accept at least a pointer to type x. So over here, yeah, integer pointer. And then, as you mentioned, we do have to set an ampersand over here to pass in its address, right? We're also going to have to go do a little bit of code modification over here because of the change in type. What should line 54 change to? Just have to add some stars some places. Yeah, star AR over here. And now since this expression over here is star AR, this expression inside size of should be star AR, right? One more star. Then we have this guy over here, AR at I. How should we change this guy? You can't do ampersand, right? You can't ask for the address of something. Like the address of like Davis is 1 Shields Avenue. So we could try to remove the ampersand at this point, right? And you can see it stops complaining. Types matches up, right? We want a pointer to an integer, right? And we said that brackets, right? These are our ninja dereferences, right? So AR at I's type is integer pointer. So types are matching. Let's give it a shot. So we'll try setting our breakpoint here again, and we'll see if we get through it. I need to redebug. So make sure you also, every time you go and debug again, and you've made changes, that you rebuild your executable, because otherwise you'll be debugging your old executable but looking at your new source, and that's very confusing. So we go through, right? I is 0, and we got the first one. Second one, seg faults. I know, right? Life is good. You're like, man, Matthew, how can you make so many mistakes in these like 5 lines of code? The first line, good, right? Second time through, this will cause it to crash if we run this line of code. And what you want to do a typecast here, or? Because I'm not sure what you mean by integer pointer I. I less than. No, this is good. Oh, yeah, that is one. No, should know integer star, because the type of star AR's type is integer pointer. Which is so this is an integer pointer. This is int, which makes sense. I'll let you know the problems on line 56. There's no typecasting. We talked about this problem today in class. Like this. Okay, getting there. Remember we talked about this, right? We have a pointer, not a star outside of it, but this, like, if we look at the type of this expression, star AR's type is integer pointer. Then we do star AR bracket I, the type of that is star AR bracket I. Remember, brackets are a secret integer, right? Remember the dereferences remove a star from the type. So the type of this expression is integer, right? So we have the right integer, but we want its location. So ampersand AR. And you're like, man, that looks kind of nasty, right? Remember that we also said that ampersand and dereference are inverses of each other, so they cancel each other out. So if we rewrite this expression without using the square brackets, we write it with just the pointers, this would be something like the address of star AR, right, plus I dereferenced, right? And notice, what do we have right next to each other? The canceling art part. So we could rewrite the expression inside there as just AR, or just star AR plus I. Well, the front lights are off, and I don't think Light stop. Is that better? Worse? Is it because of the blue that's there? Or is it because it's just light? Oh. Can't do too much. I mean, I can turn off these lights too. Is that better? The only thing I can think of doing.
I'm more for this.
So you want some more like this?
That's great.
Oh, you want some of this? Okay. So we could, do the address of AR at I, or we can do star AR plus I. Those are both equivalent. Use whichever you feel more comfortable with, whichever one you understand the most, right? They're both valid, but just remember, the ampersand and the stars, they negate each other. So now we should be able to do something like set a breakpoint on line 70, not 70, 71, and actually debug. I'll turn off this breakpoint. And hey, we got there, and we didn't crash. And if we look at AR, it's no longer null, which is great. And if we PAR bracket 0 at len, hey, we got the values there. There are still 10 more bugs in this program if you feel like playing with it, right? But these ones right here, the ones that we all just went through right now, those are the most common bugs that you guys will make with pointers, and they're also like very, very subtle too, right? We forgot the size of, we forgot we needed a pointer to the thing that we tried to change, we forgot that we needed to dereference that pointer to the thing that we wanted to change first before indexing it.
Alex.
The only reason I can kind of think about like maybe using malloc is because its interface is a lot more similar to realloc, and that realloc specifies the space in bytes. But if you wanted to, you could make your own like my recalloc, right? Yeah, like where I made my own calloc, you could make your own like recalloc if you wanted to, where it took those two arguments, and then you just call your own function that does that, so you don't screw up. It might also just, be like around for like, because people use it in the past, and since it's been used in the past, it's just kind of like carried around and just kept living because of that. Would you guys have any questions about debugging? I think the next bug is actually like pretty easy to find, which is kind of cool. So let's say like, hey, we debugged our program and we think there's no bugs in it. And so we hit the debugger again, and boom, hey, we have a segmentation fault right here, and it stopped us right at this line, right? So you might want to inspect the values of some of the variables here to see like which one seems suspicious. So, right, we can see that len is 7, and we can see that i's value is negative 75,785. That one seems a little bit off.
Isn't it?
Yeah, that's the mistake, right? The small mistake here is that I did minus I instead of plus I, right? But the cool thing here is that we had the segmentation fault, and if you just run your program, it'd be like seg fault. That's all you'd get back out, right? But here it's going to be like, oh, the seg fault happened on this line. But again, the mistake might not be with the line of code that the seg fault happens on. Happens somewhere else. So hopefully you guys all use this. If you come to office hours for help, I'm going to ask you to use this. I'm going to ask you like what you found when you used it first. So, make sure you're practicing with it. It's a really, really helpful tool, and it will save you a lot of time once you become comfortable with it. There are there are problems that you'll encounter in the world later on where you can't use a debugger for it, and you have to resort back to print debugging. These might be problems that involve a lot of concurrency, so you have multiple threads running at the same time. Sometimes under these situations, if one thread gets there first, everything is good. If the other thread gets there first, things start to break. And so now your bug only happens some of the time, and you never know when. So you got to print things out. Or a lot of times, like in production software, you just have to log everything that's happening going on, and then you have to look at the log files of what happened and like rebuild the situation from there. And so hopefully you're putting a lot of good information in your log files to figure out what's actually going on. So if there are bugs, you can go locate what they're at. Any questions here? Otherwise, we're going to start talking about strings. You guys haven't gotten that yet. Okay. So C strings are just arrays of characters that end with the null character. So they're not special. They don't have a type like they do in Python, unfortunately. And so you're not going to be able to get like really any more useful information out of them than like any other array. But the key thing about the C string is it's an array of characters that ends with a null character. And that null character is this /0 character. There is a library of functions, though, that works with strings called string.h. And we're going to go through and we're going to write some of the functions that are defined inside there. The other thing that I want to point out is with scanf, there's also a %s option, which will read a string. And a string will be a sequence of non-white space characters, and it'll store it into the space that you've made for it. When you're reading strings this way, you have to be very careful because the space needs to be pre-allocated, but you don't know how big the string's going to be, right? So if the user enters something that's larger than the space that you allocated, then you're going to like have a segmentation fault or a buffer overflow attack potential where someone could like do bad things to your program. We also, though, showed today in class how you could read one character at a time, allocating space for it as it goes along to reading a string of any length. If I enter a name longer than 50 here, bad things will happen. So how do you stop reading at white space? So the string does not read white space. It reads non-white space characters. The other thing to notice is that, notice like in the scanf statement, we just have a name here. And that's because the type of name itself is a pointer, right? And remember, scanf wants pointers, locations in memory to store the results. So it wouldn't be ampersand name here. That would be wrong. And you get segmentation faults if you did that. Or if you turn on like the compiler errors, it will tell you that, hey, that's wrong. So the first thing that we want to do is strlen. Strlen finds the length of a string. So if we were trying to find the length of our string, how could we do that? Given all you get is the array of characters. You cannot do size of. Right? We're trying to write strlen ourselves.
Start going through /f.
Yeah, until we find the null character, right? We said it's an array of characters that ends with a null character. And so all of these string functions are going to revolve around the fact that the null character needs to be there. And if it's not there, you don't have a C string, and these functions stop working, and you might get seg faults or other weird behavior. So strlen looks like this. Len equals 0. While the character that we're on is not the null character, add 1 to the length. And then once we finally reach the null character, right, we leave the for loop and then return len. Any questions here? So strcopy, what it does is it takes source and it copies it over to destination. When you do this copy, you need to ensure that destination is large enough to hold source. If it's not large enough to hold source, bad things happen. Again, you're probably going to get segmentation faults or other weird undefined behavior. So any ideas of what you might do here? Copy all the characters from source over to dest. Okay. Not quite, because you can see our arguments here are char dest bracket source bracket. That's saying an array. Or we could have declared them as char pointer dest, char pointer source. Those are both equivalent. We already assume that dest has sufficient space made for it. That's the same, like when you use the library function, there has to be sufficient space to copy it over, right? It's not going to make any space for you. So we assume that dest is big enough to hold the result. So we need to go through each character of source, right? And we need to move it over to dest until we hit the null character. So we go through each character until we hit the null character. And we move that character from source to dest. We just copy it over. And then at the end, make sure to put that null character. Because the way we've written our for loop right now is it's not going to copy it over. Make sense here? So there's also like a stir end copy, which copies the first n characters from source to dest. But if n is reached, but if the string is shorter than n, it will copy the entire string over. If the string is longer than n, it will copy the first n characters. So here you can see here stir n copy for I equals 0, I less than n. Dest.I equals source.I. If source.I equals the null character, break. Hopefully that makes sense. There's nothing too complicated. One thing to note though is that with stir n copy, if you copy less than n characters over, you don't copy the null character over. So for example, if we had Batman was our source, we set n was 3, we only copy the first 3 characters, BAT. Did we form a string? No, there's no null character, but this is how it behaves, so be very cautious. So what will tend to happen is on these pieces of code is like right after you would do like some stir copy, like stir copy into some array, Batman 3, stir n copy. And then what's going to happen is we would see like array at 3 would be equal to the null character. And this guarantees the null character gets set. If the string was a little bit shorter, right, we'll have 2 null characters. But you've seen all these functions stop at the first null character. So everything's completely fine, right? But if there was no null character in there and we only got bat, B-A-T, B0, 1, 2, our third character is not going to be the null character. So we actually form a string. So if you ever see stir n copy, it probably should be followed up by this line right here. The next function is stir n cat, or stir cat, and what it does is it takes the characters from source and adds them onto the end of dest. And again, like stir copy, there needs to be enough room for the entire string you're about to form there. If there's not, bad things happen. So what we do is we find out how long destination is. And then we go from I equals 0. We don't want to until we reach the end of source, right? Then dest at destlen plus I is equal to source at I. This should not be an integer here. Boy. Dest at destlen plus I equals source at I, right? It'll copy it over past the end of the original string. And then we make sure that we add in the null character once we're done. This piece of code here, does this look similar to any other code we just saw? That looks a lot like this. Wouldn't you agree? The only difference is this one has just I instead of like destlen plus I. So what you could do is you could use pointer arithmetic to actually use my stir copy. But instead of starting at the beginning of dest, we start destlen characters in when we start a copy. So we could have replaced this with just this function call. Do you guys have any questions on the function call? Okay. And then there's a stir comp. A stir comp compares string 1 and string 2. If string 1 comes before string 2, we need to return a negative number. If string 1 comes after string 2, we return a positive number. If string 1 and string 2 are the same, we return 0. And when we're doing our comparisons, the character comparisons are going to be based off of the ASCII table. So it might seem weird, but like big Z comes before little a. Because little a has the value 97, and big Z has the value 90, and 90 comes before 97. If you wanted a case-insensitive comparison, you have to make all the characters in both strings like either lowercase or uppercase to get that case-insensitive comparison. And there is no like 2 upper or 2 lower on an entire string. There is a 2 upper and a 2 lower on a single character, and it'll give you the uppercase or lowercase version of that character. And so you can like rewrite the string, or you can make like a copy of it. Yeah, you could do it manually character by character going over it. But remember, like if you replace the original characters, the capitalization is gone that was there, which may or may not be okay depending on your program. So there's two things you could do. One is you could create a copy of the original string, right, and then make it all lowercase. Then you could go from there. Another option would be you could write your own version of string comp, where you call two upper or two lower inside of it, right, before you compare the values. No. So like here's an example of string comp. So you have like for I equals 0, right? We want to keep going while neither of them have reached the end. And you're like, well, if str1 comes before string 2, we need to return a negative number. So I'm like, okay, -1. Or if string 1 is greater than string 2, we can return a positive number, which I returned 1. But don't check in your program against 1 and -1. Check against less than 0, or greater than 0, or equal to 0. And then you can see I was kind of tricksy over here in this final return value. I subtracted the characters, right? So let's say we ended this because both of the strings were the same. That would mean string 1 at I and string 2 at I are both what? The null character, right? So something minus itself will be 0. Great. And we got the right value. If string 1, if the characters happen to be different, right, we can do string 1 minus string 2. But if string 1 has a smaller value than string 2, what do we return? A negative number, right? For example, if we did something like if our character was like capital S and capital W, we would do like 83 minus 87, which is -4, and we get back a negative number, which would be great, right? But if string 1 comes after string 2, we would get a positive, right? Because you have a larger number minus a smaller number. And a lot of these statements right here could be replaced with this subtraction if we wanted to. Like if they're not the same, return their difference. And it would be a little bit simpler in terms of implementation, but it might be a little bit harder for people to understand. Even this might be a little bit confusing for people here. Do you guys have any questions? Okay, good luck if you decide to work on your homework. We will eventually cover everything, be able to do it, I promise.